In this video, we'll talk about differentiation and integration of power series, which are really the main reasons why we care so much about these objects. So power series are super useful in a lot of different ways, mainly because of the fact that they are nice with integration and differentiation. So assume that we have the power series, f of x equals sum from 0 to infinity of a sub n x minus c to the n, and has radius convergence r that's bigger than 0. It could be infinite, I don't care, but at least it's bigger than 0. Then what do we know? Well, we know that the function f of x is both differentiable and integrable inside the interval of convergence. So it's both differentiable and integrable on the interval from c minus r to c plus r if r is finite, or the whole real line if r is infinite. And I can differentiate and integrate these term by term. And that's where the benefit really comes into play. What does that mean? Well, that means that f prime of x I can write as the sum from n equals 1 to infinity of n times an times x minus c to the n minus 1, where I've just differentiated the x in every term of the expression, right? Because if I differentiate x minus c to the n, I get n times x minus c to the n minus 1. I've gotten rid of the 0 term because that would be a 0 times an, so it's just 0. Similarly, I can integrate term by term. So the integral of f of x dx is given by the sum from n equals 0 to infinity, an over n plus 1, x minus c to the n plus 1, and then plus a constant, where again I've now just integrated each term of the normal power series expansion. And then as a final point, both of these new series have radius of convergence r. What that means is that if I want to find a different power series, I can get them by differentiating and integrating as well. So as long as I know that my series converges on a certain area, I can then differentiate and integrate on that domain and see what happens to the power series there. This is why this is super useful, because I can sort of replace my function f, which might be nasty and terrible to use, by its power series, and its power series is basically a polynomial that I can integrate and differentiate really easily and use that instead if my f is so terrible that I don't want to handle it normally. This also gives us new tricks for finding power series expansions. So let's look for finding a power series expansion for arctan of x, and want to figure out also where this is valid. So what's the property of arctan that makes this really easy to do? Well, the point is, if I look at arctan and I differentiate it, what do I get? I get 1 over 1 plus x squared. Well, that looks really good. That looks like a power series I know how to write. So 1 over 1 plus x squared, I know is the sum from n equals 0 to infinity of negative x squared to the n. Right, I'm rewriting this as 1 over 1 minus negative x squared, and I can plug it in that way. Where is this valid? Well, this is valid whenever absolute value of x squared is less than 1, or when x is less than 1. How do I get to my answer from here? Well, now I need to integrate both sides. So then arctan of x should be the antiderivative of 1 over 1 plus x squared, which means I don't need to integrate this power series. And to make this easier to write out, I will split the negative x squared to the n into negative 1 to the n and then x to the 2n. Well, now I just integrate this like normal. This is basically a polynomial that goes on forever, but it's still a polynomial. This should be sum n from 0 to infinity. I have negative 1 to the n over 2n plus 1, x to the 2n plus 1, plus c. But since arctan of 0 is 0, I want to get rid of that c and make it 0. So this becomes my power series expansion for inverse tangent, and it's valid on the same range as the one before, as value of x less than 1. Notice, arctan is a well-defined, nice function everywhere, but this series only works for x less than 1 because that's where the original one converged that we were dealing with before. So I can't extend this beyond x equals 1 because the series won't converge at that point, even though arctan is still a nice function beyond x equals 1. So that's the idea of using derivatives and integrals of power series to talk about other power series we can write out, as well as why power series are so useful in other applications. Because we can differentiate things term by term, that's where solid differential equations comes into play, because once you can do that, polynomials are really easy to handle, a lot of functions aren't. And this gives us an easy way to handle these sorts of functions that we don't want to deal with directly. So this fact that we can differentiate and integrate power series term by term is super useful, and it's why we care so much about them and use them in these different physical applications.